This camera is just going on our
for a while. Okay. Oh, already live, right? Start. Okay, hopefully everything works now. So welcome back to linear algebra. And I'll remind you that we spoke about linear combinations last time. Meaning, what can I create from a given set of directional vectors? And we said that this was a bit of extra, but this is for a few examples. I think this one is a good one. We were given two vectors, 1, 2, 3, and 4, 5, 6. And we asked whether 1, 2, 4 is a linear combination of these two vectors, meaning can I get to 1 to 4 using only V1 and V2 and the operations? You can multiply by any scalar you like, and you can sum up two vectors. And then we generalize it and say, okay, so if I have a general XYZ, can I get under what conditions can I get to XYZ from 1 to 3, 4, 5, 6? And we found out that we will be able to if and only if x minus 2y plus z is 0, which is exactly a plane, which makes sense that the set of vectors that you can get to from two directions is an entire plane. And the set of all the points you can get to is called the span. It's the linear space, linear vector space created, so-called, from these vectors. I'm not sure if I said it, but I'll say it now at the beginning. Second, which number lecture are we at? Oh, 9. Okay. Nine. The set of all vectors that can be created from V1 to Vn is called a span. The vector space span by V1 to Vn. This is the set of all linear combinations of these vectors. So that is span. You're the right class, Thomas. And looking confused. Span, that doesn't have anything to do with me. Okay. Homework exercise. Prove that the span is a subspace of the entire vector space. And another definition, the span of the empty set is by definition only the zero vector. It is a subspace, but what I'm saying, it's a bit confusing as to if you just take the empty set, and I'm telling you that the span is the zero vector, how can you know the zero vector of what vector space, right? Is it the zero of the plane, the zero of the three-dimensional vector space? So given, I'll change it up a bit, given a vector space V, we define the span of the empty set to be the zero vector of that space. In general, when I define the span, we must have had some vector space and some field from which we take the vectors and the scalars. So I think in the empty set, it's a bit more confusing, but always when I calculate the span, I must know what is the field, where do I take the scalars from, and what are the possible vectors. In any case, the span of the empty set is the zero vector. It's just a definition. It doesn't follow from anything that I said, because I said that the span is everything you can create. What can you create using nothing? So if I was God, that was something else. But as a mathematician, what can I create using only the empty set? I don't even use the empty set. Using all the elements within the empty sets, using nothing. So by definition, we say that the zero can be created, okay? It's helpful for definitions. It's not a mathematical claim, but rather a definition that makes everything easy. For instance, I can tell you, I don't remember if I told you, but what is the idea behind dimension? It's the number of vectors needed to create something. In order to create a line, how many vectors do you need? One. So it's one-dimensional. In order to create a plane, you need two vectors. It's two-dimensional. In order to create a point, the origin of axis, how many vectors do you need? So by this definition, zero. And then the dimension of a single point is zero. It makes sense. It's nice to use. Okay, so that's why we defined this that way. Okay, so we saw the concept. We saw the concept of creating spaces from given vectors. Next, we need to define the concept of unnecessary
No, with
double N,
A.
1C, 2S. I wasn't even close.
It's
The concept,
double. It's lots of doubles.
yeah, unnecessary.
There's like a way of remembering it.
Yeah.
You get thought about it in-
It's completely unnecessary.
Yeah, I was
Yes,
going to say.
yes. Okay, wow, I was really surprised now. Okay, next we need to define the concept of unnecessary vectors. What do I mean? I'll give you two quick examples. Say you have the vector 1, 1, and you also have the vector 0, 0. What does this set create? What is the span of this set? It's a line, and it's the line of all elements, AA, such that A is a real number, right? Who is unnecessary here?
0, 0.
Yes, obviously, 0, 0 is unnecessary. Yes. Okay. So we need to define it. When I'm saying obviously, it's a bit confusing because it's not obvious at all because I didn't define what unnecessary means. But I mean, but I'm saying in human speak, what was the need of 0, 0? It didn't tell us anything new, right? What about the span of 1, 1 and a -2, -2? What do you think about that?
Either close before the necessary.
It's also the same one. There's something extra here. We won't actually pinpoint and we say this vector is unnecessary. We may do sometime technically, but in general, the term will be linear dependence. We'll say there is something extra here unneeded. And why? We wish to define dimension. So we need a set of vectors that we can create everything with, and there is nothing extra. And that set, its size will be the definition of dimension. A plane can be created by 2 directions, and any other direction will be unnecessary, it will be extra. Okay, that's the idea we're going, but we need to mathematically define the 2 concepts in order to state what I said accurately. Okay, another example, which is less obvious, I think. If I take the span of 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I've shown you this example a bunch of times. It's the same as just 1, 2, 3, 4, 5, 6. You remember it by any chance that the last vector is within the same plane? Right, so again, there is linear dependency. Okay, so next we will define exactly what do I mean when I say linear dependence, and then I will phrase and prove a proposition that will connect the definition that we will have, which is kind of dry and technical, to the idea of an extra vector. Aiming, I would say that there is a linear dependence if and only if, in some conditions, one of the vectors can be created from the others. It's true in general, but I will phrase a very specific theorem that will help us in the future. Okay, so definition, given a sequence of vectors within a vector space, obviously, v1, v2, 2v, k, doesn't we say that the sequence are bombing, right?
Yeah, no,
I'm
you're not
looking at
insane.
Bombings, Israel, whatever. Linear dependence is harder. We say that the sequence is linear dependent. Dependent? Isn't it? Dependent? Oh, I'm surprised.
Dependent.
I'm writing it, like that? No.
No, dependent.
Depend. Dent.
Just.
Yes. Yeah, I just came from the dentist. Actually, just the cleaning. Do you have a name? In Hebrew, it's called shinanit. It's usually a woman, but it mustn't be. It doesn't have to be. That cleans your teeth.
When you go to the dentist.
But I didn't go to the dentist.
No, here you go.
In here, we call it
your teeth.
shinanit. What? I'm not sure
I
if
don't
there's
know.
if it's a concept. I'm sure it is, but okay, sorry.
I only did it in the army, so they make you bleed more.
When you come just to someone that cleans your teeth, it's not a
Your
dentist.
toothbrush in your bathroom, like
What? She comes to your home. No, like deeper cleansing.
it's like a thing.
Yes.
They are the dentists.
Yeah, and they're not a dentist.
Do you go after
It's
the
a
dentist?
it's a
Or
whole
like
No, no.
occupation.
No, you
That's
go
really
you go when you need to clean your teeth.
Yeah.
Right.
How do you know when you need to clean your teeth? When
No,
the dentist
every
tells
now
you?
and again. No, you have to. They recommend that you go like 4 times a year or something like that. Twice a year depends on how much money they need. But it's a thing here. Okay. Whatever. Given a sequence of vector, we say that the sequence is linear dependent or linearly dependent, whatever. If there exists color, not all zeros, such that A1 V1 plus AK VK is the zero vector. So it's not totally clear why does that grasp the concept of an extra vector, like I said. Like I said, we'll prove some proposition behind it in a second. But try thinking of it, the vector is supposed to be the x's. Try thinking about it. You walked some distance in the z direction, then you walked some distance in the x direction, and then you walked some distance in the y direction. Can you imagine that you ever get back to the origin? And the answer is no, because if I walked in different independent directions, one cannot cancel the other. That's what this definition is basically saying. If walking on this direction, I can make a so-called full circle and get back to zero, that means that there is something extra here. Okay, that's I don't know, philosophical notion more than a mathematical argument. The mathematical argument that connects it to this case, I will tell you in a short while, but that's the definition. So the next question is why they took, and then if you want to ask Sami, why take such a weird definition instead of the obvious one that say without this vector, the span remained the same. So it's technical. If I claim that if I define that linear dependence says that one of the vectors is unnecessary, then I must check every one of the vectors whether it itself is unnecessary. This definition does it at once. And also because it's a homogeneous system, you get a matrix, you Gauss eliminate it, and so technically it's very easy to use this definition. It's harder to grasp why is it defined so, but technically it's easy to work with, and that's the reason they defined it this way.
Sorry, I didn't understand the phrasing. Dependent if there exist colors.
Are linearly dependent if there exists colors, not all zeros, such that, right? Because if you go zero distance to z, zero distance to x, and zero distance to y, obviously you remain at zero, right?
Oh.
If all the scalars are zeros, then obviously this will be zero. That doesn't tell us anything.
But you mean all not zero?
No, not all zero.
Okay.
There exists one that is not zero.
Okay.
Yeah. This is like logically the hardest definition in linear algebra because it's two quantifiers, right? There exist scalars such that not all of them is zero, and this is false.
And it gives you zero.
And the summation is zero. The linear combination is zero, exactly.
I mean,
So it's two quantifiers, there exist and for all. And compared to calculus, that's nothing, but compared to most of the definitions, yeah, that's the first one that it's complicated in linear algebra. And it's not just the first one, and now it's starting to be this way. This is the one, some proofs around it are confusing, but we don't go any up, any
worse.
yeah, low, I would say. Yeah. Yes, Sammy.
What's the difference between linear dependence as we've just defined it and just a line in vector space?
What do you mean line?
Shape of a line
This
on a plane.
this is a linear depend. This sequence is linearly dependent because there is a way to create zero from these three vectors. It doesn't just have to be a line like here. Here it's quite obvious. If we multiply the first vector by 2 and the second vector by 1, if you sum them up, you get 0. That's linear dependence, right? But here it's not as clear as to why there is linear dependence, and it's not a line. The first two vectors create a plane, and the last vector is contained within this plane. And that fact makes it's true that there are some scalars such that the combination will be 0.
But why do we call it linear dependence then? If there are like three things lying on a
Rather
plane?
than just dependent? No, because it's linear algebra.
But,
Every vector is a
but a
line.
plane isn't linear. A plane is
No, plane is linear. No, so
Plane
you're
is
wrong
linear.
about. We're in linear algebra. Vector spaces are linear algebra. So linear in one, what you think of linear is one dimension. Plane is two-dimension linear, and
Right.
three-dimension linear.
It's a
It's
cube?
it's everything. Yeah. So it's silly. But it's not a cube. It's an infinite cube. It's the entire universe, right? It's confusing.
If you didn't say linear, you would be talking about non-Euclidean
Yeah.
geometry, and that's
Yeah,
not what
yeah.
we want to talk about.
Yeah. But so it's really hard for me to go higher dimension. I can just go these three. A dot is a zero-dimensional linear space, which is not interesting. It's just a zero vector. The two interesting cases that you can imagine in your head is the first dimensional, which is a line, and the second dimensional, which is a plane. But all of what we're doing, and like I said, that comes from geometry, and then it takes its own algebraic form, and now everything that is a vector space is called linear.
right.
Okay.
No, I get it. It's just in my head because linear comes from the word line.
A
Line is a
Never thought of it this way. I never thought of the origin of the word. I just know that linear means linear algebra, and I know these are vectors. So for me, linear are vectors. I never thought of it as a line. Yeah, but no, not just a line. Anything flat maybe is a better word.
not curved.
But yeah, but still in three dimensions, it's not flat.
Maybe everything's
Is
straight.
it curved?
Straight.
Maybe, yeah. And why is it straight? Because the only two operations you can do is multiply by a scalar that continues straight in the same direction, or add two vectors which take two straight lines and take the line in between, right? This is, and I showed you, it all came from Newton, and that's exactly what he wanted. The forces are linear because when you force, just a quick thinking game. If you have a straw in looking like a snake, okay, and you put a spitball in it, and you go, okay. When the spitball, it will go round and round. Eventually, it will come to the end. And how will it get out of it? Can you show me with your hand its movement after it leaves the straw? Spitball went like this. This is the end. Where does it continue?
Straight. Tangent.
Straight, right? The tangent, perfectly. People who are younger or don't know may say like this, right? Like Galileo, what he thought. But it's around the ocean, and it will continue around. But Newton, that was the first thing that he really changed. Say no, everything continues straight. So that's the linear, right? So I like the word straight for linear, but it doesn't mean just a line. It could be within a two-dimensional space. Each force by itself is a line, but if you have a few forces create something more complex.
Yeah, you just can't make a curve in linear algebra because it's a sum of infinite vectors.
Yeah, exactly, because the curve demand you choose you change, excuse me, your tangent at each point, right? So that's much more complex. That's not linear anymore. That's calculus. Okay. So that's the definition of linear dependence. Let's do a couple of quick examples. Example, 1, 2, 3, 4, 5, 6, 7, 8, 9 is dependent since one time 1, 2, 3 minus 2 times 4, 5, 6 plus 1 time plus 1 time 7, 8, 9 is 0, 0, 0. So we have linear dependence here. The emphasis is not on the linear, but rather on the dependence. There's something dependent here. 1, 1 and 0, 0. And another example, 1, 1 and 0, 0 are dependent since 0 times 1, 1. I am allowed to multiply by 0, but I'm not allowed to multiply only by 0. And what can I multiply 0, 0 by?
Anything.
1. Yes. So that's 0, 0. And again, we have the linear dependence. Okay. Another example, 1, 0 and 0, 1. What do you think about these two?
They're independent.
Are independent. And I think that is a point in time which I need to give you the Hebrew term for the next semester. Linear algebra 2, do you take in Hebrew or in English? Oh, still in English? I'm not sure if that's important, but it's a shorthand and you won't guess it if you don't know. Independent is batal, since it's בלתי תלוי לינארית. Okay, and dependent is tal, which is תלוי לינארית. Yes. Batal, not betel. And are independents. And how do we know that they are independents? Since consider an arbitrary and null combination A1 1 0 plus A2 0 1 equals 0 0. We must show that all scalars are 0. So the question was whether you can get a nullifying linear combination when not all the scalars are 0. So I'm taking an arbitrary null combination, a linear combination that goes to 0, and ask, is it true that all the scalars must be 0? And here it's in fact really easy to see, because on the left-hand side you get A1, A2 equals 0, 0. And indeed, A1 must equal A2, that must equal 0. So this sequence of vector is batal, linearly independent. Yes.
The quantifiers for the past one was or exists a denomination of A1 and A0 such that
Not about logic for Thomas. Linear dependence says that there exist scalars A1 to AK such that not all scalars are zero. How can I write it? I didn't write.
Why
Not
not
for every I, AI is zero. And the combination A1 V1 plus AN VN is zero. I did with K before. Oh. Do you agree so far?
It's not easy to just write exists one AI that is not
So,
zero.
Sammy says that this is equivalent to there exists scalars A1 to AK. And there exists an I such that AI
Doesn't equal
is
zero.
not zero, and I could put a parenthesis many different ways. Maybe this is easier, and this sum. Yeah, that's true. It's the same. I think the first way to look at it, it's easier, but the second is true.
I was going to tell you maybe to take out the for all I out of both and just do for all AI not AI equals zero and for all AI the sum from one
But it's not true. I don't demand that all of them is not zero.
Mhm.
I just need one of them not to be zero. So what is a linear independence?
the
The
negative
opposite of that.
Yes, great. What is it?
for
That's
all
like
for all
for all
A1
A1 to AK.
All of them.
What is the opposite
Wait,
of not something and something?
so all of it. Oh,
What's
wait.
the
Or.
negation of n? Is the or of the negations, right?
Yeah.
The modal. So
Or.
one way to write it is for all I is zero, or the sum is not zero. And that is quite confusing. That's not the best way. That's not the way we look at it. And this is equivalent to what is not something or something?
not or do you mean
Not P
Isn't it like implies?
or great. Q means P implies Q, right? We use that. So we say if for all A1 to AK, the fact that the sum is zero implies that all the coefficients are zero, that's linear independence. And that is the way I just described linear dependence in the example above. Look at it. I said, let's take an arbitrary null combination. For all A1, I'm taking an arbitrary null combination, and I wish to prove that it implies that all the coefficients are zero, all the scalars are zero, and that's exactly what I did. So yeah, I didn't say it for just. This is the most complicated definition in linear algebra, and it is something that some students have some problem with because it's logically more complex than other things. It's not horrible, in my opinion. It's not like the definition of a limit, but it's still more than you used to. Yes, Sami.
I'm confused with the order of for the first predicate, the second predicate. I'm confused with the
This
order.
one,
Yeah, I'm confused with the order of the like
I'm saying
the
there
such that-
exist colors
such that.
such that and everything else. Such that not all of them are zero, and the combination is null.
So. Okay,
And that's the definition as I wrote it, right? It's called linear dependence. Look at it.
so technically there aren't two
Given a
predicates.
sequence of vector, we say that the sequence is linearly dependent if there exists scalars, not all of them zero, such that the combination is zero.
So technically there aren't two quantifiers, there's one quantifier and two statements.
The way it's a lot of the time, it's about how we say it, because that's like what you said. You say, but instead of saying not all, we could say exist. But I still regard it as two quantifiers because it's over different domains. This is a quantifier over the scalars, and this is a quantifier over the chosen scalars, right? I already chosen scalars and I quantify over them. So it is, however you twist it, there are two quantifiers there. But yeah, it's a lot about how you mention it, how do you phrase it. You can phrase things equivalently, and sometimes it's easier to understand in one way rather than the other. But it doesn't change the fact that they are equivalent, right? So for linear independence, we usually use this one, and for dependence, we usually use this one. That's why I took a sum and I showed, oh, there is a coefficient who is not zero. Not all the coefficients are zero. You can say this is rather the same. I don't know. The difference between the first two, it's not important. It's kind of the same.
I would always get confused about using OR for stuffs that are exclusively true, because either they're all zero, or
Yes.
yeah,
You're right that in this case they're exclusively zero. Exclusively. You have to accept it. Because if you don't accept it, then you cannot accept the Morgan. Because the negation of the and is not so, it's the mathematical one. But it doesn't really matter. It's not I'm not quizzing you again on logic. In a sense, I am, because you need to use your logic, but not like specifically. And not such high logic. Okay. So I promised you a proposition and I will propose to you.
I don't think I'm ready for
Proposition.
that, yeah.
Why did you say you're going to do
take him out for a coffee first.
yeah, no. No? Decline.
Yeah.
Okay, proposition. Given A1 to AK, which are independent. So we have K vectors which are linearly independent. And given a vector, okay, something very confusing here, so I'll try to reduce some of the confusion. I'm talking about vectors. Up until now, when I wrote A1 to AK, I usually meant scalars. In the next proof, we'll have a set A and a set B, and it's so easy to call the vectors A and B. Okay, so I'm A1 and AK here are vectors, not scalars. And if A1 and AK are the vectors, if I use scalars, I will use C1 to CK. Fine. So if I have a K independent vector, and given a vector B, such that B is not one of the given vectors. B is not A1 to AK. Another vector. Then A1 to AK plus B is dependent if and only if. So I had a sequence of vectors with nothing unnecessary. And I added an extra vector b, and now suddenly it's dependent. Why? What would be the reason for that, in your opinion?
Could make B out of the vectors. we
Yes,
already
and how do I write it? You're completely correct. We can create B using A1 to AK, that's the statement. And how can I say it?
have.
I'll help you start. B is a member of the span. Yeah, exactly. Right? Because this is the set of everything we can create. And this is more about language, but that's linear algebra language, right? B is in the span of A1 to AK. Okay? Any questions so far?
Are you going to qualify this statement, or are we going to leave it at that? Like,
No, I approve. I will prove it.
okay.
Proof, yeah. I'm not even sure I need this. Let me think about it for a second. If I add, because it depends in whether I phrase it as sets or sequences. And I think I don't need this. If this is dependent, then B is in the span, obviously. If B is in the span, yeah, I don't need that. But the reason I phrase it, I change my mind every now and again, or between phrasing linearly dependence in sets or sequences. What is the major difference here? In sets, and a vector could not appear twice, and then I must have told you that it's not already there. But because I'm writing a sequence, so I didn't give it as an example, but the sequence of 1, 1, and again 1, 1 is dependent. If you repeat a vector, then you obviously have the linear dependence. So, but because I'm saying sequences, and I don't have to have this extra condition here, and now I will prove it. And I'm just saying this connects between the two ideas. This is the idea of something unnecessary, something that can already be created, so why do you need it? And this is the technical definition using linear and null combinations. And I'm proving they are equal, they are equivalent. Okay, and the proof is quite easy, to be honest. Proof. So because it's if and only if, we need to prove the direction. In the first direction, first assume A1 to AK, then B is dependent. By definition, what does that mean?
That you can make B out of the.
No, that's not the definition. That's what you want to prove. What's the definition of linear dependence of vectors?
The
Scalar combination. There exists C1 to CK and CK plus 1. Right? There is an coefficient to B as well. Not all 0. Such that C1 A1 plus CK AK plus CK plus 1 B K plus 1 is 0, the 0 vector.
No, B is not BK plus.
Right, you're right. Okay. And now I wish to show that we can create B by the other vectors. Can anyone guess how can we do it? How can you create B from the other vectors?
You can send B to the other side and set it negative, like it's negative CK1B,
Yeah,
and then
everything else.
and then divide by what?
That's CK.
Am I allowed to divide by CK plus 1?
because it's
Yeah, but it could be 0.
no, because it must be 0. You know that the dependent one is B.
So how do I say it?
You know.
If CK plus 1 is 0, then C1 A1 plus CK AK is 0. Agreed? And one of C1 to CK is not 0. Agreed? Because not all the scalars are 0. We assume that this one is 0. So the non-zero one must be one of these. Agreed? So what's the matter with that?
So that means that there's a dependent vector from C.
Not dependent vector. One vector is not dependent. It's always a sequence. The sequence is dependent.
Sure, so there's a vector that it makes the sequence dependent, which is in
That's it.
contradiction
Yeah,
to the
exactly.
declaration.
And don't say there is a vector dependent. That's kind of what, to be honest, that's kind of what this proposition promises that you can say from now on, right? You can say one of the vectors is dependent, right? But before we prove that, we can only speak about the dependence of the sequence. But this is a dependence of the sequence, right? Therefore, CK plus 1 not 0. And we can divide by it, right? That's, we have field, we have an inverse for every number different than 0, right? And get and obtain that B is equal to minus C1 over C K plus 1 times A1 plus CK. Second, use the space here, which annoys me. Plus, it's not plus, it's minuses. Minus CK over CK plus 1 AK. Which means by definition that B is within the span of A1 to AK. Because I created it using these vectors and some scalars.
Is it okay to make B equal to a negative sum? Shouldn't it be positive? I mean, you can set it to whatever, yeah, I know.
Yeah, but also think of a negative as just another direction. Everything is about directions here. So negative is not really a negative thing,
Yeah.
right? It's the other way around.
Yeah, no, I'm just saying, like,
That's what I'm saying. It's the whole scalar is this. The whole scalar is this. Just say when you go on this axis, instead of going to the positive side, go to the left.
yeah, I mean, just like you could set B to be a positive vector and still would be linearly
No, there is no such thing as a positive vector. That's my point.
Yeah. Sure.
The entries could be positive, right? But for the vectors are directions, they're not positive or negative. Think about you when thinking of numbers, you can also might say that there are no really positive and negative numbers because there are numbers in this direction, number in that direction. Positive or negative is would be.
I don't think
I
we're
don't
ready
know.
for that.
If you change your way, so is positive or is positive negative? I don't know how much you weigh. That doesn't matter. In vectors, the direction is the main thing. Positive or negative, just say in that direction or 180 degrees to the other side. Okay, it's the definition. Okay, on the other hand, assume B is within the span. What does that tell us? That tells us that we can create B by some linear combination of A1 to AK. Agreed? Take the B to the other side, and you get that 0 is C1 A1 plus CK AK plus -1 times B. Agreed? This is a null combination. Are all the scalars 0?
No, because we have -1.
Exactly, with the last scalar different than 0, and therefore by definition A1 to AK and B are linearly dependent. Great. Definition
Please zoom out a bit.
one.
Please
Ah,
zoom
zoom
out a
out,
bit.
sure.
Thanks.
Giving Sammy some time to copy from the board. Then I will define a basis. And then I will ask a question. We'll take our first break. Next week we don't have class.
Why not? Oh, Shavuot.
Shavuot, yes.
I thought we were just going to bring cake.
Cheesecake. And then we have 4 more classes. I think it's enough time to finish cover the material.
Yeah, good.
I'll make sure of it as we go along, but we are, like Pilot says, we made up time in the air. I always, by the way, it's always my manner to start slowly and then increasing. But I think the start is the most important stuff. After you have the general ideas, you can go a bit faster. But we will see. I talked about with Tomas in calculus. I'm sure that we'll cover the material. In linear, I was a bit less sure myself, but I think we will.
Good.
Okay, so definition, given a vector space V and the subspace U we say the sequence of vectors, I don't know, let's call them W's, as they don't get any affiliation yet. Do I wish them not to get an affiliation? It's true either way, but okay, I'll continue what I said. The vectors W1 to WK within V are bases for U if the following 2 conditions hold. 1, the space spanned by W1 to WK is exactly U. That means, by the way, the W1 to WK are contained within U, they must be contained within U, but moreover, everything in U can be created using W1 to WK. It's poleset in Hebrew, it spans. That is enough direction to create everything. But what is the second cooling effect condition? What else do we require?
That W1 and WK is independent.
Exactly, W1 to WK is linearly independent. These are the two things that when they hold together, they form a basis. And my first question, main question is, given two bases for a certain space, why there can be two, any two vectors within the plane which are not on a straight line would be a basis. So there could be a lot of different bases. I'm not sure if it's bases or bases. Bases is
Bases.
Right.
it's just bases, the same thing, plural.
Yeah, I don't know.
Bases, maybe.
Yeah, yeah, whatever. It's not really, in Hebrew, it's the same word, basis. We don't have this problem. But in English, it's base and bases, which I'm not sure what it is. In any case, given two bases for you, what will I ask about the two bases?
That their span are the same.
The what?
Their
No,
span.
that's by definition the span is the same
Okay.
because the span is you. But what can I ask about that? You have two sets of vectors which are form a basis for the same space. What do you suppose the connection between them will be?
If you smush them together, will they be a basis too?
It won't be because
They're
will be
independent.
dependent, right? You added the extra. No, but not together. Do they have the same cardinality?
Really?
Meaning base number of vectors, right? It's not Aleph Fs. Right, I'm asking, do they have the same amount of vectors? Could it be there is a basis with two vectors and another basis with three vectors? And the answer I will just tell you, and after the break, I'll prove to you. But it must be the same number, and that number is defined to be the dimension. How many vectors there are in the basis? Okay, enough for now. Let's take a break until quarter past.
I think I will take.
Oh, I just went and I realized that the pizza was good for them.
It says double check whether the noun is singular or plural. And
Is it gender
he
neutral? No, I didn't.
suggests basis.
Is it gender neutral? Yes.
Yeah. Oh.
Okay.
Yeah, he didn't
It never came up.
yeah. I'm disappointed.
Gender.
Stuck in my head.
Were you not born when that song came out?
Probably not. I started listening to that entire album. Wow, that's so good.
TLC.
Mm-hmm.
Yeah. Okay. So that is our question, and now we wish to formulate a couple of claims that will help us answer it. And the first is Steinitz. I have no idea how to write it. Steinitz lemma. And given a vector space V and two finite set of vectors. You know what that, and two sequences of vectors, which we call A and B. When I'm saying a sequence, it must be finite. I'll write the word finite. Two finite sequences of vectors, we'll call them A and B, which are both contained within a vector space. And then for every sorry, another assumption. Also assume that A is independent and B spans all of V. We have two sets of vectors, two sequences of vectors, A and B. A is linearly independent and B spans everything. So for every vector A within A, there exists, again, the logic complexity, a vector B within the sequence B, such that B.
When we say B spans all of V, we mean span of B equals.
Yeah,
V.
exactly.
Okay.
Such that B is not within A without A. In simple words, if we'll remove the vector A from A, B will not appear there. And if we remove A from A, and on top of that, we add B, the new set is independent. In Hebrew, we call it lemma ha'achlafa, the replacing lemma, because we replace A. So why did I need to tell you that B is not already there? All right, note, since B is not within A without A, then the cardinality, the number of elements in A, is equal to the number of elements after the replacement. Why do I need to be able to do such replacement? You will see afterwards. but that's what I wish to do. I wish to, for every element of A, I can replace it by some element of B. And later you will see why is that ability is important. And what's more, it remains independent. So I can replace it by some other vector.
Well, that makes sense, no?
Yeah, it makes
Because-
sense. Yeah.
Because V spans V.
Exactly, I agree. I agree. B spans everything, everything is within B, so everyone has a replacement, right? Everyone can be replaced. That's exactly what it means. The proof needs to be more formal than that, but it's not clear as why do I care about it, and I will just tell you generally, because I wish to look at two bases and tell you they have the same amount of elements. And the idea will be that otherwise you can take elements from one basis and replace it with the elements of the other base, and you will get a contradiction this way. You will see the contradiction later. But my intent is to be able to talk about two different bases. And bases are independent, and spanning. So you have two bases, it's completely fine to assume one is independent and the other one is spans the entire vector space. And you will see. Yes, Thomas.
What does it mean for a vector to be in a sequence of vectors? Because
Like a set.
no, yeah, I just mean when you say this vector is in this set and this vector is in this set, you can have two different sets of vectors that have the same span, even if their elements are different. So if you're saying
Yes.
B
That's exactly the point. A and B could be very, very different. They could be mutually exclusive. There is no single vector which is in two of them, but still they are all within the same vector space.
yeah, but taking A being linearly independent and taking saying B is not in A minus vector A, you could have two different vectors that represent the same direction. and
Yes, yes.
how-
But what I'm saying is that there is some vector such that it's independent.
you'd say there exists.
There exists, yeah, I didn't say all, definitely not all. There exist, okay? So, proof. I have another closing bracket. Okay, proof. What? Oh, I pressed the wrong button. Proof. Assume by contradiction that it's not for now a moment of logic. The argument is for every A there existed B such that. What will be the negation of that?
Analysis.
There
A.
exists
Will be.
an A vector an A but A vector. Oh, it looks wrong either way. There exists an A in A
Such
No,
that
that works.
such that
A minus A, you know,
no. For every A there exists a B. So the negation is there exists an A
that for all B.
such that for all B
A minus A union B. It's not independent.
such that for, but there is an and here, right?
Or
Exactly. Such that for it is true that a lot of logic here. And B is in A without A, or A without A along with B, or if we replace B with A, is dependent. Agreed?
The thing in English is that you can say and it could mean implies in some cases.
Yeah, yeah. The Hebrew is same. There are many. If you say I don't give a damn about him, or you say I give a damn about him, you mean the same thing, although it's a negation of the logic theorem, not theorem. What we said it's called sentence, logic sentence.
In this case, you negated one, but you didn't negate the other.
No, I negated them both. Here it says independent,
Ah,
and I switch. I can't negate the set, right? But I said the claim was the set is independent, the negation is that the set is
the
dependent.
complement is the independent.
Yes, the complement. Yes. What is the negation of everyone in the class are smart, everyone outside the class are stupid? No, it doesn't work that way. Okay. And so in any case, note that in both options, B is within the span of A without A. Why? Add one way is that B is actually one of the vectors, and therefore it obviously can be created by this vector because it's there. You can multiply it by 1 and the others by 0. But if this is dependent, that's the proposition I proposed to Sami before. If we took an independent sequence and we added a vector and suddenly it became dependent, it's because B can be created by the vectors that were there. That's the proposition I wrote before. So in any case, B can be created in A without A. Since every vector in B is contained, let me write it mathematically. Since the entire set B is contained within the span of A without A, you remember what we assumed about B?
That it has every.
That it spans everything. So then also the span of B is contained within the span of A without A because of
Definition of
no סגירות. What
closing.
Yeah,
Closure.
closure, yeah, because the closure property, if B is within there and that's a subspace, then whatever you can create from B remains within the subspace, but the span of B is V, is the entire vector space. So, and who specifically is within V? Which one vector is interesting?
A.
A. Therefore, specifically, A is within the span of A without A. What does that tell you?
That A is in the subspace.
No.
And
You have within the set A some vector that can be created from the others. What does it tell you about the set A? If you can create one vector from the others, it's dependent.
I mean, yeah, that's one of the.
By contradiction.
Aren't all subspaces independent?
No, subspace is very much dependent. You're confusing. Subspace is huge. it's the whole line, it's the whole plane. There are infinite number of vectors in it.
Mhm.
I'm talking just about a small set of vectors, right? And
The
if you
span-
can create one of them by the others, that's linear dependence.
Yeah, no, but the span.
The span is infinite, yes.
The-
But I'm saying the set A, not the span of A. Set A itself is dependent. Why? Because one of the vectors can be created by the other.
Sure.
And again, it's all the proposition that I told you before, that if you and if the last vector is spanned by the other vectors, then there must be linear dependence. Okay. So why did I need that? Now, proposition. Assume that A 1, 2, A, K is independent. No, sorry. A1 to A K plus 1 is independent. Then B1 to BK cannot span the entire vector space. I've worded it in a very specific way, but the idea behind it is that there cannot be a more independent, a larger set of independent vectors than a set that spans the entire vector space. Okay, and with that, I will prove that every two spaces must have the same amount of elements, because both of them are dependent, independent, and span the entire vector space, and therefore each of them should be smaller than the other, and therefore they must have the exact same amount of elements. Okay, and the way that we prove it is just using Steinitz's lemma. Why? Proof. ABC assume by contradiction that B1 to BK does span the vector space by Steinitz lemma. We can replace every vector in A1 to A K plus 1 by a vector from the spanning sequence. So first of all, replace A1 by B1. So we'll get B1, A2 until AK plus 1. And what did we promise with Steinitz? We said for every element of A, we can choose some element of B such that when we replace, look at what I did here. I took A, I took the first element, I removed it, and I added instead of it an element of B. And what are we promised about this new set?
It's linear independent.
It's independent, right? Such that this is Therefore, this is independent, assuming B1 is the B from the lemma. That's just a matter of labeling, right? I'm assuming that the one I called B1 is the first element that pops when I use the lemma. And after I replaced A1 by B1, this set is independent. Who can I replace next?
So,
A2. Next, we replace A2, so we have B1, and then comes B2, then A3, until AK1 plus 1. And when will it all end?
When we change AK.
AK, yes. Is independent. And finally, we'll get B1, B2, BK, AK plus 1, independent. Does that make sense that this sequence is independent?
Because by Steinitz lemma, but yeah.
Yeah, so on the one hand, it makes sense because due to Steinitz, but I'm hinting that it's a contradiction. What does it contradict?
That the size can be different.
No, that's what I wish to prove. What's the contradiction here? There is a contradiction here. You need to find it.
No, it would be a contradiction if we could change AK plus 1, no?
No. I'm saying this is a contradiction. And that's just a matter of size because we have, I'll hint, because we had too many independent vectors. After we used all of the BKs, there is one remaining. And
Yeah,
why does it not make sense?
Because you said that it's independent and spans the whole vector space.
Yeah, B1 to BK, it spans everything. So specifically, it spans AK plus 1. It couldn't be independent.
Mm.
Since AK plus 1 is contained within the span of B1 to Bn, or BK, we get a contradiction. Steinitz lemma says for every vector we can replace it, and if the sizes didn't fit, then after we finish replacing all of the vectors, what can I do with the last one, right? I need to, that's another way to look at it. I need to be able to replace it as well. There's nothing to replace it by because I already finished the entire spanning thing. Okay, and we get a contradiction to Steinitz. Any questions so far?
I was thinking, can you do a direct proof or does it have to be a contradiction? Because like you're saying, you're changing one by one and you get to the end and it's not independent, but it's like by Steinitz rule, you just directly say if you try to change, then.
No, but the change works. It just at the end you get some problem. Because okay, change everything direct without assuming by contradiction, and after you change everything, you say okay, change it. What's the problem, right? There's the wording may have been different. I do agree that I could say no, but no. In order to use Steinitz, I must need the contradiction because Steinitz assumes that it spans everything.
Mm.
That's what allows me to do the replacement. So yeah, I don't think I could word it differently.
No.
Okay. And so conclusion. Given two finite bases, and they must have the same number of vectors. Y, proof. Since assume B1, B2, are such bases, since B1 is spanning the entire of the vector space, then and B2 is independent, then this number of elements in B1 must be larger or equal to the numbers of elements in B2. That's what we proved. We said if we have an independent set, a smaller set cannot be spanning. So if B1 is spanning, it must be at least the size of the independent set or even larger. And symmetrically, and so is the number of elements in B2 larger or equal to the number of elements of B1, because the basis, I'll remind you, is both independent and spanning. So once I can say, because this is spanning and this is independent, this must be larger. But because this is independent and this is spanning, this must be larger or equal, therefore they are both equal. Okay? Definition. Given a vector space with a finite basis, its dimension is defined to be the number of vectors within the basis. And it's a good definition because every two bases have the same amount of vectors. So it couldn't be that the dimension is such if you look at this basis, and it's such and such if you look at that basis. All bases have the same amount of elements. Any questions?
So if something is spanning, it must be independent and vice versa.
No.
No?
No. In a three-dimensional space, if you take four vectors, it will be dependent. I will say something in that manner in a second. And definition. A vector space is called a finitely generated if there exists a finite set and that spans the entire vector space. I must give you an example for you to understand the definition, but we are speaking about the difference between finite dimensional space and infinite dimensional spaces. And in this course, we'll only deal with finite dimensional spaces. Or for example, if I take, I don't know, R3 is a finitely generated since R3 is spanned by the unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So I can span it by three vectors. It's finitely generated, but Rx, which is the set, which is the vector space of all polynomials, is not finitely generated. hence there is always a higher power. It's not a religious thing, but if you take any finite set, look at all the polynomials there, one of them has the highest degree. What about degrees other than that? There cannot be created using linear combination. So that is an infinite dimensional space, which we don't deal with. We will deal with finitely generated spaces. And my next theorem is theorem given a finitely generated space V, it must have a basis and it must have a finite basis and therefore a dimension. Every finitely generated space must have a basis. The question is, we define a basis as a set that you can create everything from, and it's also independent. And natural question is, should there always be such a set? Maybe this vector space is curved or crooked, and that's kind of the linearity of it all. It couldn't be. If it's finitely generated, you must be able to find a finite sequence of vectors that creates everything, and nothing is missing. If the space was curved, it wouldn't be true, right? Because I don't know, in some specific direction, you will have limitation and such problems. But luckily, it's not the case. And I will prove it. Proof. And start with the empty set. We call it A0 is the empty set. It is independent. And if it spans the vector space, we are done. Okay, I'm starting with the empty set. It's an independent set. In which case will it span V? Which vector space is spanned by the empty set?
Zero.
Just a zero. If the entire vector space is just a point, then yeah, we found the basis, it's the empty set. Otherwise, there exists a vector, let's call it V1 in V, such that it is not created but by, whatever we have before. In this case, it's just the empty set. Therefore, A1, which is A0 plus V1 is also independent. Why? Because if it was dependent, it means that the new vector we just added is a linear combination of the other vectors. It's all about the proposition I proposed to Sammy before. We always can come back to that idea. If we are adding a vector and it's become dependent, it means that we already created beforehand. And if we cannot create that, it means that adding it keeps things independent. Continue this way. And by adding in the vectors independently, could we continue to infinity without finding a spanning set? I'm saying I'm starting with an empty set which is linear independent, and as long as I'm not spanning everything, keep adding things, and it will always remain independent. Could we continue it in perpetuity without ever stopping? If it was infinitely dimensional space, the answer would be yes. But since it's a finitely generated space, the answer is no. Why not? What says that the number of independent elements couldn't be too big?
Generality.
Well, no, we proved before here that if you have k plus 1 independent vector, then a set of size k could not be spanning. You can never surpass a spanning set.
Right.
But since it's finitely generated space, you do have a finite spanning set that you can never surpass. No. Because we can never surpass the size of the finite generating set. There is such one. So every finitely generated vector space must have a basis, because you keep adding linearly independent vectors, and at one time or another it must be spanning, because otherwise you could add vectors in perpetuity and surpass the size of the spanning set, which will cause contradiction. And so we have basis and we have dimensions. Any questions so far?
I didn't fully understand what we were trying to prove here.
There is a base, there exists a base.
Or the finite
Yes.
vector space.
Yeah.
Okay.
You just add vectors, and you must be able to stop. You must stop sometimes, and the only reason that will stop you is that you span everything. Because if you didn't span everything, you can add another vector and continue to grow. But there is a cap. There is a bound on how many times you can do it, but because it's finitely generated. If it wasn't finitely generated, then yeah, you can continue. With polynomials, you can add 1, then x squared, then x cubed, and so forth. And every new power will be independent by the previous powers, because it's an infinite dimensional space. But when it's finitely generated, you can never surpass the size of the spanning set. Okay, because of the theorems that we proved. Today, I think we proved the we learned the toughest subjects in this, maybe one of the 2 toughest subjects in this course. It's the proof that the definition and proving that we do have a dimension. It's the number of vectors. It is not affected by which basis do I take. A plane basis will always have 2 vectors, whichever basis you take. Another conclusion. Given a vector space V such that its dimension is n. So it's a finitely generated vector space. We have n vectors that spans it. And assume and given, I don't know, assume it and given two sets A, B, which are contained within V, such that A is independent, and B is spanning. What do you think you can say about the sizes?
dim B is equal to the other B, like the dimension of B is the same as n.
B and A does not have dimension. These are just sets, finite sets. So how many elements could there be in an independent set? Is there
Less or equal to n, you mean?
exactly? The number of elements of A never surpasses the dimension, and the number of elements in the spanning set is always surpassing the dimension or equal, right? It's all from the same set of theorems, because we said, because when I'm saying that dim V is n, I'm saying there is a basis with n vectors, so it's both independent and spanning. So it caps all other sets in both directions. And proof, homework. Try to prove to yourself. It follows immediately from all that we said today. Try to write it and understand why is it so. Okay, and lastly, שלישי חינם. משפט השלישי חינם. Let me think about it in English. The 1 plus 1 מה זה מבצע?
Plus one.
Offer,
2 plus 1 offer.
but it's not 2 plus
Yeah, you pay for 2 and you get the third one free.
the 2 plus 1 offer.
Yeah.
Okay. Fine. Given a vector space V such that its dimension is n. And given a set S contained within V, then if any two of the next three holds, then the third one holds as well. You get the third for free. That's why in Hebrew we say shlishi chinam. Okay, for any two, you get the next third. And the three are the number of elements of S is exactly n2. S is independent. 3. The span of S is the entire vector space. Proof. So 2 plus 3 implies 1 by definition, right? if S is independent and spans everything, then it's a basis. Therefore, the number of elements should be the dimension. That's the definition of dimension. Assume 1 plus 2 if the span of S is not all of V, we can enlarge the independent set S such that it surpasses the dimension by, and that's contradiction, because an independent set could never be more than the dimension because it surpasses a spanning set, and that could not be, as we proved. And lastly, and it's very similar, assume 1 plus 3. We have n vectors that can create everything if S is dependent, then we can remove one vector and remain and get a spanning set smaller than the dimension, again by contradiction. And what we said before, a spanning set must be larger or equal to the dimension, an independent set must be smaller than the dimension. Okay, another finite thing, I think let me make sure that I'll go over it, that I didn't forget anything, but I'll just tell you and then I'll make sure. When you wish to prove in discrete mathematics the two sets are the same, what did you need to do? How do you prove the two sets are equal?
You subset something.
Two-sided inclusion, right? In linear algebra, you have something that is sometimes easier. You get one-sided inclusion and the dimension is equal. So that will be the next theorem, that if you have two spaces, one is included in the other and the dimension is equal, then it must be the same space. Okay? And it sometimes helps to prove the two spaces are equal. And before I write it, I'll make sure that I didn't miss anything in the chapter. I think I did not. And then we'll move on to the, I did miss something in the chapter. משפט הממדים. And also the spaces of matrix. Okay, let me make sure that's all I missed.
Determinants is the next one.
No, I told you determinants are not in this course.
Actually.
Yes, but you asked,
Three
you're
times.
surprised. No, but you're surprised each time. That's
No, because some of the homeworks, I research how it's proved, like generally.
research. I asked ChatGPT.
No, I math exchange, which is usually worse.
Yeah.
And then they're like, use a determinant, and I'm like, I cannot.
Exactly. Just making sure this I did. This I did. That is irrelevant. This I just taught you. This is what I'm about to teach you. Yeah, the next thing I was right on order. משפט הממדים, I will do it in a bit. Yeah. So finally, I did remember. Okay, fine. But we are moving forward very good. Okay. So proposition, given a vector space V and the subspace U, then if the dimension of U equals to the dimension of V, then U equals V. So when I'm saying it's a subspace, that's one-way inclusion. Right. One-way inclusion and dimension. That's a shorthand to remember that you don't need to do two-way inclusion always. Sometimes you do, but sometimes you can just say U is contained within V, so it's a subspace, and their dimension is the same. There must be the same space. Okay? You cannot have another two-dimensional space within the plane except from the entire plane. Okay, there is no such smaller two-dimensional space. And the proof is really easy, assuming you understand what I said before, right? But look at the proof. Assume dimension of U equals to the dimension of V, and mark it by the letter N. Therefore, there exists a basis U1 to UN for U. Since U is contained within V, then U1 to UN has number of elements as the dimension of V and is independent. If we have an independent set of the size of the dimension, what did we say by the 2+1 offer? What can we deduce? That they span by 2+1 offer U1 to UN spans V. We knew it spans U because it was a basis for U, but it must also span V. Another way to put it, if U1 until UN does not span V, then it means that there is some vector that cannot be created with them. If we add that vector to the sequence, it will be a larger independent set which surpasses the dimension, and we learned that that is impossible. Therefore, thus, U, which is the span of U1 to UN, also equals V, which is the span of the very same vectors. Okay, if it didn't span everything, then you could enlarge the independent set. Any questions thus far?
I'm just thinking we're going over a lot of stuff and my brain is like half power right
Yeah,
now.
that's what I'm thinking, whether to continue and lose you all, but then say, believe me, it's true. Well, no, I will prove it, but the question is whether to assume that you listen to what one word that I said.
So my contradiction.
Yes. Let me think for a second. Because there is also not a lot of things to give examples about. Because when you think about the geometry, you know, everything I said here is so trivial. I'll try to give you a few examples. For instance, look at the set, consider the set, 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 1, 1, and 1, 0, 1, 0. Is, oh, sorry, and -1, 2, -3, 4. Oh, great. Let me name it A. Is a dependent or independent set. How can we know? We have any idea? Is this a dependent or independent set?
It's dependent
Why?
because you can make the last vector from the last first to last, right?
How? I don't see it. But in any case, I'm looking for a quicker answer than calculating and making. We can, and I will do an example like that as well of saying if something is dependent or not. But I'm saying the answer here should be quick and painful. Yes, Sammy.
Well, first, can we take out 5, 6, 7, 8?
Why?
Because you can make 5, 6, 7, 8 from 1, 2, 3, 4, and 1, 1.
How?
By multiplying 1, 1, 1 by 4 and then adding.
For an adding, okay, you're right. But still, I'm not looking for a calculation. That's true. But I'm not looking for a calculation. I'm looking for a swift answer.
No,
Why?
I don't know, you said so it's not correct.
Yeah, no, I prefer a swift, correct answer. Because you already seen it's dependent, right? Even the first three, as Sammy said, are dependent. I didn't do that on purpose, but it's true. But why can we say?
Because it's 4 and 5.
Exactly, that's what we learned today. It's dependent. It is dependent since these are 5 vectors within R4. And what is the dimension of R4? Dimension is 4. There could never be a larger set, a larger independent set than the dimension. You have more elements than the dimension, that it must be dependent. That's one of the main things we proved today. And how do we know, by the way, the dimension of the R4 is 4?
There's
No.
four.
1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1 is a basis 4 are all 4. And
Because they're the unit vectors.
what?
Because they're the unit vectors.
It's not because they are called the unit vectors, but it's true because it's easy to see that they span everything, right? If you multiply it by A, B, C, D, you will get a general A, B, C, D, and it's independent. Homework to prove that it's linearly independent, it spans all of R4. But how many vectors do you have here?
4.
Since these are 4 vectors, the dimension is 4. Let me give you another example, which I find interesting. Example. What is the dimension of all polynomials with degree smaller or equal to 2? Basically, it's lines and parabola. Quadratic function. So what would be the dimension of all polynomials?
It's 3 or 2?
That's the question.
It's 3.
It's 3. It's 3. Why?
Because you have x to the 2, x to the 1, and x to the 0.
Yes. All of the ax squared plus bx plus c such that a, b, and c are real numbers is the span of 1x squared. Do you agree that it's the span, right? It's a times 1 plus b times x plus c times x squared. Is that linearly dependent? Independent, sorry?
Yeah,
Why?
because I mean, they're not in the same space. X to the 0, x to the 1, x to the 2 are.
That's the question.
Mm.
How are we sure 1x squared are independent?
Because the sum of them, like the sum of the vectors times the coefficient, if they're not all 0, it's not going to be 0.
Take an arbitrary linear or a null combination, meaning a times 1 plus b times x plus c times x squared equals 0. Can you deduce that all of the coefficients are 0?
I mean, deduce, yes, because
How?
I mean,
What?
because no number in the field, multiplied by
Discriminant is
1x or 0.
Then there's solutions.
No, you don't know this discriminant.
I mean, x,
Right.
like if x would be in the field of the coefficients, then maybe, but I don't think it is.
I think it makes sense it is, but I don't think it really matters. So that's a rather a confusing question. It also has to do with calculus. If we have in general, say 3x squared plus bx plus 1 equals ax squared plus 2x plus c. What are a, b, and c?
Phase 3, phase 2.
How can you be sure? Obviously, I agree with you that if you plug in A3, B2, and C1, it will hold. But
that isn't an
must-
identity.
Must A equals 3, B equals 2, and C equals 1?
Yeah.
Why?
Because on the left side, on both sides, all the polynomials of degree I is grouped together under the coefficient of whatever that coefficient is. There's no other on the right side.
Yeah,
there's no
but
other
why-
x squared term.
But couldn't there be some other combination that altogether creates the same graph? Right? I agree that if 3 is 3 and 2 is 2 and 1 is 1, they're obviously the same term. But maybe 3x plus 7 is 3x squared plus 7x plus 1 is 4x squared plus 2x plus 10. Some other combination that gets to the same number eventually. Right? How are we sure that the coefficients must be the same? They are the same, by the way. I'm not arguing with that with you, but it's not clear at all. And there is a very neat trick to prove it. I will write this as a note. And I'm just finishing it up here. Therefore, A equals B equals C equals 0. And in the note, I'm explaining why. Derive both sides 2 times. If you derive the left-hand side 2 times, let's think of what happens. What happens to 1 after you derive 2 times?
Goes to 0.
0. What happens to bx when you derive 2 times?
Goes also to 0.
And what happens to 3x squared?
Goes to 6.
It goes to 6. And on the right-hand side, what do you get after you derive twice?
You get A6. And the other is 0.
You get 2a.
Okay.
And therefore, A is 3. Then you can subtract, then you can cancel 3x squared equals 3x squared, and continue by induction. Yeah. There are other ways to prove that, but that's a very calculusy way to do it. It's not at all clear when are things dependent or independent, like sine and cosine. How am I sure they are independent? And the trick with deriving often works. There are other tricks as well, but with functions, derivative often solves the problem. Any questions so far? Sam, you appear to be confused. Yes.
But if wait a sec, let me just think before I say something. Yeah, if C is 1 and B is 2 and A is 1,
No, A3.
no, up there. Top.
Here,
Yeah.
A is 0, B is 0, and C is 0, because on the right-hand side you have nothing. Right?
Wait, what is the question? What are we trying to?
We're trying to prove that 1x and x squared are linearly independent. So we took an arbitrary null combination, and we needed to prove that all the coefficients are 0. And they are indeed 0, but I'm asking, how do we know that they're 0? And what I'm saying is that because the coefficient of 1 on the left-hand side is A, and on the right-hand side it's 0. The coefficient of X on the left-hand side is B, and on the right-hand side it's 0. Right? It's kind of like the same question written here, only here none of the numbers is 0.
Maybe I'm
Think
getting. Maybe I'm
straight
getting-
on this one. If you derive twice, on the right-hand side you will get 0. The left-hand side, what will you get after two derivatives?
2C.
2C. So C is 0. And then by induction, derive once, you get B, B is 0. And finally,
If
A
you were
is
to do
0.
X, if you were to say C is equal to 1, just humanly,
Yes.
C is equal to 1, B.
Oh, sorry, yes. I tried to humor you. Okay, yes.
It didn't work.
It did, okay, yes.
C
Yeah.
is equal to 1, B
Yeah.
is equal to 2, and
Yeah.
A is equal to 1. And you've got x squared plus 2x plus 1.
So it would have a solution. Some X will solve it,
Right.
but you wish it to be the 0 function, the 0 parabola, which is always 0, not just sometimes 0. I think that's what confuses you.
Yes.
Say there is some X for which it will equal 0, you're right, but it's not the 0 function, right? If we look at the vector space of all polynomials, the 0 polynomial is the 0 function. It's the constant function that sends everything to 0. Other polynomials could be 0 every now and again, but still not. It's kind of like within a vector, you have a 0 coordinate. It doesn't make it a 0 vector, right? So it's kind of like that.
So what we're asking here is does the combination of c squared plus bx plus a1, sorry, cx squared plus bx plus a1
Could be the 0 function. For all X, it must be 0. The only way is if all coefficients are 0. No other way.
is there a symbol for the 0 function?
No.
That should make one.
You're correct that it's confusing. I think in that case, I will write, like I always write the 0 function, I can write the 0 of all polynomials. Right, that's some way to say it. It's the 0 polynomial. It's not just the scalar 0. But yeah, this is confusing. This is confusing. Okay. Like, by the way, when we talked about the notes, I'm not looking for the fact that some time during my speak the air pressure is 0. 0 note is when the air pressure is constantly 0. Then there is no sound. No. It doesn't have to be 0, because if the air pressure was 0, we would explode. But it should be constant on some number, not 0. Okay. And any questions so far? So I think that's more than enough for today. See you all in 2 weeks. No, see you all in 4 o'clock after work.